Hello, thank you for having me. So my talk today is on pragmatic microservices for the rest of us. So I've been exploring microservice architectures, moving into that space for the last 4 or so years at EventMobi. If you haven't heard of EventMobi, we are an event technology platform building tools for event organizers to improve their events. So if you've used the event app for the conference today, then you've already experienced our technology. If you haven't, I suggest trying it out. It's your companion for an event like this one, where you can get the agenda, the list of speakers, build your own schedule, and carry that around in your pocket with you. All right, so first, let's define microservices so that we're on the same page. Because I think there can be some confusion in this space about what microservice architecture is and isn't. And it's going to be a lot better if we're kind of on the same page here. So these are 3 types of architecture that I'm kind of using as a comparison here. So I think the monolith on the left, everyone's probably pretty familiar with at this point. That is your single runtime, single language, single framework, single deployment. Generally, the majority of your code in one place is what we call monolithic architecture. This is generally a fairly simple approach, or simple at first, at least. But it can have some scaling challenges, especially if you end up having a large number of developers, large number of teams, and they all need to merge into the same repo, deploy the same code base repeatedly. There are certainly ways to scale it, but it can be a bit difficult. The middle architecture, which I'm calling specialized services here, I feel is the one that's probably the least well-defined in the industry, although it's actually a very, very common architecture. This is when you have distinct services, usually anywhere from a couple to a dozen, that are focused around one capability, whether it be technical or business. This architecture kind of naturally arises when you have, say, a monolith, let's say like a Django, and you have some capability that you need that it's not very good at. So let's say you want to build out a WebSocket solution, and you decide to build a node service to handle that for you. You end up building that on the side of your monolith. The two might then talk to each other, usually over HTTP. And you might end up developing separate owners for them, separate deployment ways of deploying them, separate ways of monitoring them, logging them. And they kind of move out in these distinct ways, focused on these 2 different runtimes, their 2 different needs. Then maybe later on you add Celery for asynchronous processing, and you get a 3rd service. And it kind of goes that way, and they build up. Now, I think the distinction here between this and the microservice architecture is that once you have enough of these, they become difficult to manage. And that's because when you're first building these out, you're not necessarily thinking about standardization or shared infrastructure tooling for these services. The microservice architecture is one that supports hundreds to thousands of services. And it does that by establishing a set of standards around things like communication, discovery, configuration, as well as supporting infrastructure so that you can make things like deployment, logging, monitoring, resiliency really easy. You want to be able to write these things or throw them away and rewrite them in around a day, maybe a couple days if they're complicated. And the majority of the developers in your organization will be writing these things. It should be very easy to approach. You don't want everybody to have to resolve these complex challenges that go into coordinating all of these services with each other for every service that they build. So it requires a very kind of mature organization, I think, to really fulfill that sort of microservice architecture. And that's why I think the specialized service architecture, while a very effective architecture, and probably a lot more reasonable for the majority of organizations, is not really microservices in my view, and mixing the terms can lead to confusion. So microservices are, maybe a good fit for solving a lot of problems, but as I mentioned, very difficult to get to unless you are a large organization with a lot of resources. So there's somewhat of a middle ground, which here I'm calling in-process microservices. So the goal here is to take as many of the advantages of microservice design as we can and apply them to a monolithic process for the sake of simplicity. So the goal is we get the design principles of microservices without the complexity overhead of building out a distributed system. This allows us to start taking on some of the challenges of microservices in terms of building out those communication paradigms, those standards, supporting structure, one at a time, without having to tackle all of those up front before we start rolling out our platform architecture. So I'm going to use our architecture as an example for how we did this. This was an evolutionary approach. We did not set out to do this. We did not set out to do microservices at all in particular. The goal from the beginning was to build a Python API to start replacing our legacy PHP monolith. So it started out just very focused on how do we make writing REST APIs really simple? And then how can we kind of keep the components inside this architecture decoupled enough so it doesn't kind of turn into a mess like our previous legacy system kind of did. And as those ideas matured and evolved, it slowly moved more and more towards borrowing these principles of microservices that kind of were rising up in the industry consciousness at the time. And after a while, we ended up here, which ended up being a good fit for our business and our needs. So I'll go more in detail here. Flux is the name that we use internally for this Python project. The top layer is Flask. That is handling our web requests. But that's about it. It just is the outer layer, and very quickly it hands off to our internal architecture and is not interacted with very much after that point. We have an HTTP adapter, which understands what REST is and can convert it to the internal language of the rest of the system. We have a Flux client, which is a component that interacts with service discovery, which is a way of registering, locating, and retrieving the reference to all the services in the architecture. The Flux client is able to talk to service discovery, find the target service you want to talk to, and knows how to communicate with it, whether that service is local or remote. Any Python project can run Flux client. And so that's used both internally, but we also use it in external Python scripts that run in places like CircleCI or our tooling or separate projects. And then the rest of the architecture is many services. So we currently have about 400 of these. They each are responsible for owning a piece of data or for presenting a piece of data in a specific way or performing a specific action. And that's where the majority of our business logic, our data, in the system is. So inside of each service is a base class, which handles kind of the control flow, the framework type parts of it. There's the service implementation, which is what the developers in our company will actually write. Each of our full stack developers writes these services in their daily work to complete features. And each of these services has their own instance of a Flux client, so they can talk to any other service in the architecture. So we'll go a little more in depth on these microservice principles as they get applied in process to the architecture here. So one of the most important ones, and probably most difficult ones, is encapsulating your data sources. In a monolithic architecture, you'll probably end up more with something like on the left, where you might have two separate components, called A and B in this case, that are both accessing the same data for some purpose. So B might call into a table named A might call into a table called B, maybe they're doing a join. The problem is this is creating a lot of coupling at your data layer. What you need to be doing in a microservice architecture is more like what we have on the right, where A reads from A, B reads from B, and if A needs data from B, it goes to B to get it. This is conceptual. It's fine if they are accessing the same database, for example, but they should not be accessing the same table. The reason this is important is that each service needs to encapsulate its data so that it can make the decisions about how it implements its functionality. If you don't take this approach, there's not much point in pursuing kind of a microservice design because you'll create a lot of coupling at your data layer. You won't be able to easily rewrite your services, and you won't be able to easily change any part of your data implementation, whether it be rewriting parts of the schema or changing to a different, more suited data storage solution. So if these services need to talk to each other all the time, they need a good way to communicate with each other. So this is how it works in our system. Each of our services through Flux Client has access to this reference, depicted here as self.services. And we can specify the name of the service we want to access, so people in this case, and then we can specify an action we want to take on that service. So for the top example, we are going to the people service, we're going to create a person, and we pass in the data we want to create as a dictionary. Then we get back the person object. The bottom example here is accessing the same service, but in this case, we're going to read some data. We're specifying we want a single record back. So we pass in a parameter, in this case email, and we get back the record we're looking for. So this approach works without any imports, without the services having any explicit knowledge of any other services. You just need to know that this other service exists and that it has these actions. These actions are standardized across our system to create reusable patterns for all of our CRUD operations. It makes it very easy for all of our developers to kind of get in, get the data they need, integrate their services together without needing to understand the particular ad hoc design of any given service. So this is what a service looks like internally. Cleaned up and simplified a little bit, but this is pretty close. So at the top, we are defining a person contract, and this is going to be the interface for the data flowing in and out of our system. We're defining 3 fields here. So we have email, first name, and last name. And we're specifying some validation about these fields. We're expecting first name to be a character field. So if we get an integer, it will automatically raise a validation error for us. We're expecting it to have maximum length of 255. So if that's violated, it will return it. What these contracts do is establish a strong interface at the service layer and make validation at the service layer simple. Remember that we want to push a lot of these details out of the database layer where they're often done to the service layer, where in this architecture it matters more significantly. We don't care, a caller to the people service doesn't care anything about the implementation. It doesn't care about where or how the data is stored. All it cares about is this contract that's defined at the top here. Moving down a bit, we have our parameters, which specifies what filters we have on the service in terms of retrieving data. We define our service as a class. We give it a name and register it with service discovery in the decorator there. That's the name we'll be able to find it under. The URL parameter here is optional. It's not required in terms of accessing the service internally through Flux Client, but it does expose it as being a RESTful endpoint automatically by including that URL. A little further down is just some glue to attach the contracts in the context they play on the service. So our person is our resource in this case, and our person params are our params. And then we have the actions that the service can take, and this is what the users will implement when they're building out a service. So in the read here takes in parameters, it will search the database and return data based on the parameters provided. This is what it looks like, the lifecycle for an HTTP request. So HTTP comes in, hits the HTTP adapter, and then services internally serialize messages to pass between each other. The advantage here is that the input and output of each service is very simple. It takes a serialized JSON blob that loosely follows a REST structure. But it also means that it's completely language and framework agnostic, this communication paradigm. It's also protocol agnostic. So internally, we're passing it directly based on references. But we can also pass these service messages asynchronously. So if C wants to communicate with B asynchronously, it can put its service message into a queue. We have a worker that can grab it from the queue, pass it back into our system. The message knows how to route itself and can find its way to B. So every service in our architecture can be communicated with both synchronously and asynchronously. And it would be easy to add in additional protocols on top of this. So a third one being PubSub is something we were looking at doing in the future. And if or when these do distribute, we can find more efficient ways of serializing them and might explore something like protobufs or that kind of technology for this case. So in our previous example, if we want to create a person, but now we want to do it asynchronously, all we do in this case is put async equals true. And instead of getting back a person object, we get back a job, which lets us track the progress of it if we care to. But that's all it takes to communicate with the exact same service asynchronously instead of synchronously. For error handling, the default option would be that an exception that gets raised in service C would propagate all the way up the call stack. So if A calls B, calls C, C raises an exception, that'll rise all the way up to A. The problem here is that each service should provide a hard interface. A should not need to know that B uses C as a dependency. A should not need to know how to handle any errors that C might throw. The fan out that can happen in kind of a mesh network of services like this makes the complexity astronomical for any service to have to be able to handle the errors of any other possible service. So it's important that every service becomes a hard boundary for all communication, and that also includes errors. In this case, B has to catch all exceptions that C can throw, and then has to decide what to do with those. So it can choose to retry, it can raise a new error, it can ignore the error and continue on, but it needs to do something. If nothing is done, that will result in a 500, and we'll be alerted to that and then go and fix it. For logging, we approach it this way currently, where we log every web request that comes in. But for a single web request, we might have like say 20 internal service requests. And so we also log every service request that gets made in a similar way to logging a RESTful API call. This gives us a lot of granularity into any single request that you wouldn't have otherwise. And taking that data, if we visualize it out, we can build out a service request tree. And this is important because otherwise it becomes very difficult to understand how any of your functionality is really being implemented. Tracing through any given use case manually is going to be difficult, but tracing all of them will be impossible by hand. So being able to identify them this way is important. Here we can see, for example, that the red circle might indicate that there was an error in this service, and the one that called it maybe raised a warning based on that, but continued on. We could also identify the X10 might be making 10 calls from one service to another service. That's probably not a good idea in an architecture like this, so maybe we want to optimize that. Similarly, we could see maybe the average response time is 20 milliseconds for this other call, so we might want to go and analyze that as well. Some form of this granularity is required because without that, it's going to be very hard to track down where throughout this complex branching request tree did an error actually arise. Where is my performance problem coming from? So, should you use this architecture? As I mentioned, we kind of evolved this architecture naturally. Microservices are a good fit for our business. We have a pretty broad set of requirements that we're trying to fulfill. So we want to have many autonomous teams that can all get their work done and build their own products, but also easily integrate all those products with each other. And it ends up being a very wide footprint. A microservice approach works well for us because it allows us to solve a lot of these problems once and get efficiency out of very quickly rolling new services. But being resource constrained and not having a lot of dedicated resources for projects like this, going a full-on microservice route is just not pragmatic for us. So this kind of evolutionary approach gives us a stepping stone where we can start figuring out some of these challenges one at a time. If your business has a smaller footprint, maybe you're dealing with something technically challenging, but much more focused, then something like the specialized service architecture is probably a better fit. Because in that case, you can build out a handful of services using the technology that's best suited for the job and put a small team in charge of each one and let them sort of solve the problems as they go. It's only when you start thinking about having a large number of developers owning a large number of resources that I think these sort of architectures become important. If you're just starting out and resource constrained, I'd probably still recommend just starting with a monolith. And if you have all the resources in the world and a huge system, then you probably will end up with something like microservices eventually. All right, that's all I have for today. Thank you.
All right, so we have time for some Q&A, if anybody has questions.
Hi, Ryan. Thank you. Do you actually, for your sort of asynchronous tasks, do you did you create like a queue service for that, or using something off the shelf? Just curious.
Off the shelf. So currently we're using RabbitMQ. We're using it as a dumb as you can, first in, first out queue. Currently it's a little bit past proof of concept stage, so it definitely could use some more thought as we scale it out further, but it is being used for production use cases. Essentially, we just put all messages into the same queue. We've got a worker that pulls all messages out, passes them back in, and the messages know how to get to where they need to get to. So we started out with a very simple architecture for the async. Went with Rabbit primarily because it's proven technology. There was a hosted service provider that worked well for it. Our initial research into SQS seemed a little high on latency for what we wanted, but I would definitely use a service like SQS if it fit here, which I'll probably continue to investigate.
Hi, quick question. How do you deal with the latency when you're passing messages between all your services, especially the HTTP overhead when a service calls another service? My question is, how do you deal with the latency overheads of chaining of services?
So being in process here, we're not getting too much of that at this point. We are still getting some because this architecture does introduce overhead that would not exist in like direct library calls. It adds a little bit of latency. It does not add as much latency as each one of those being an HTTP request would. Ultimately, try and minimize the number of service requests to a degree. You don't want to put service requests in loops, for example. Instead, grab all of the data you need from your target service and merge it locally instead of looping on it. Make your internal networking fast, cache your data. pretty much optimize it as you go.
I just had a question at EventMobi. How do you make some of your decisions, like how fine or coarse-grained a microservice should be, and also when to, say, go outside of that and make a library and share that across, say, a bunch of node services or something versus another framework or whatever?
Actually, I'm glad you brought that up. That's something I want to talk more about. I think that's probably one of the hardest problems, really, in building an architecture like this, or even in software design in general, is what are your boundaries? How fine-grained or coarse-grained should your components be? And this architecture really puts those questions front and center. We kind of just figure it out as we go. And I think that's one of the advantages of this architecture, is that it's optimized for evolvability. So you build a service one way, and then over time you kind of get a sense of whether it's working or not, and then you maybe build a service another way, and you kind of get this communal group learning out of the right way to build it. As long as you make the process of changing things and refining things easy enough, then the collective will kind of find the most efficient way to build them and will kind of work out their own boundaries. Something that I've kind of worked towards to help organize that process is domain-driven design, which I think is really applicable here. And trying to find ways to loosely define layers of services and the kind of boundaries and domains that they're in, and which teams own those domains. But it's definitely a work in progress.
Just a quick question. Any ideas about open sourcing any of this stuff?
I'd love to. We actually have open sourced a much, much earlier version of this called Thorium, which is available now. That was a framework designed to make RESTful APIs in Flask really simple. It is open source if you want to check it out, but it is not like maintained or necessarily like ready for a lot of use. But a lot of these ideas originated there. If we get a chance to open source this, I would probably like to refine it a little bit more to the point where we can actually suggest, okay, you can use this and it'll be great for you. So yeah, it's something I'd like to do.
Just a little bit about a deployment of these things. How do you choose which services go into? It's all in process, I understand, right? So how do you choose which services to bundle together, and how do you deploy that to an actual VM or container instance or whatever?
So that's one of the problems we're pretty much just completely avoiding by taking the in-process route. As far as deployment is concerned, this is just a monolith. This is just a big Flask app that we can deploy the way you deploy any Flask app. No, currently every instance that we run just has every service available. That probably would be the approach I'd follow either way. One idea we've thrown around is that different teams could each run their own cluster of Flux instances. Each one might still have all services, but then they can control their own deployments a little more cleanly. Yeah, that's one of the areas that I think this simplifies a lot. It hasn't really been a problem. The only downside there is that there's a release train that everyone sort of has to get on, and we release daily to avoid problems with that. But that's where going to a kind of true distributed microservice model gives you that benefit.
Hey, I'm just wondering, what's the size of the engineering team, and how do you decide which engineers work on your microservices? Because you said you had 400 of them?
Yeah. So they're pretty small. We write them probably in like half a day, just to give you a size of the granularity. The engineering team is about 20 technical staff, actual software devs. We have product teams focused on each individual front-end product that we offer. Each of them is responsible for a domain of services that fulfills their product needs. And then shared services, we kind of determine who owns that in terms of integration. So each team is autonomous in deciding and creating the services they need to fulfill their product needs. And then we coordinate in terms of needing to access data from another team.
I'm afraid we're out of time for questions. I have one brief announcement before we break for lunch. There is a last-minute new talk at 2:25 right in this room, which is a blank space on your schedule, called Building a Hack-a-Sack by Paul Mulling. Lunch is box style like yesterday. Thank you.